So let's start today's lecture. So we are going to talk about power generation, right? How do we produce electricity? What are the different sources of producing electricity? Of course, I think basic things you know, we have seen last time that, let's say, how much was the percentage, 60% or something of the energy comes from coal, right? Or maybe 70%, 80%, there was some value which was of course higher. So coal and then gas and then nuclear, right? Of course, solar was one predominant source. So how do they actually produce electrical energy, right? So you can imagine in older times, right? You knew what a motor is. I'm sure somebody would have tried rotating the rotor of the motor and would have seen, wow, voltage produced ho gaya. And then people thought that, okay, let's now invent ways of how do we make sure that we can rotate a motor, right? And thereby operating it as a generator. So most of the energy generation happens through machines, electrical machines, right? We don't use induction motor, we use synchronous machine, and we would talk more about the synchronous machine, but predominantly if you see 20 years back, I would say maybe 98% of the electricity would have been produced by machines, right. Now because of some of the other technologies coming in, we are also producing electricity through other sources, but still predominantly it is machine. So we use synchronous generators, right, to predominantly produce electricity. All of you know what is a synchronous generator? How many of you here know what is a synchronous generator? Raise your hand. How many of you have heard the word synchronous generator here? Raise your hand. अच्छे से उठाओ. Okay, then other people have not heard the word synchronous generator. You guys were not around in the last lab which we did, 240, right? There was a big demo, you remember, where there was a huge sound of the rotation of the motor, right? You don't remember that? It was towards the end of the lab, right? There was a big demonstration which was done where there was a big machine rotating, making lot of sound, right? Some of you might have also felt a bit afraid going closer to that motor because it just makes so much of sound, right? That was essentially a synchronous generator. Now how many of you remember it? Raise your hand. Still, okay, some of you remember it, fine. So we'll learn more about synchronous generator, right? But before we do that, let's see what are the different ways in which people rotate the prime mover. You understand the terminology prime mover, right? Prime mover means the force which is rotating the shaft. So if we start with coal, right? Coal is of course a predominant source of electricity. Nuclear is also quite a bit in general used for electricity production, right. In both the technologies, what you do is you create heat, right, either through nuclear reaction or by burning coal, and then you use that heat to convert that heat into some way of pressure. So what it means is if you have a boiler, right, filled with water, and now if you heat it up, then what will happen? This will convert into steam, right? This steam will fill this remaining part, and of course steam would be expanded. So this would be at much higher pressure, right? And now if you make a small hole from here, the steam will come out from here with a lot of pressure, the way it does it in. कहाँ पे होता है? You have seen this ना somewhere? देखा हुआ लग रहा है ना? Pressure cookers, right? Yeah. So once the steam builds in, it just comes out, right, with a big force. And now if you can use it, if you use this force, right, this pressure to run a turbine, and the turbine rotates the shaft, you connect your generator will rotate, right. So this is predominantly what happens in coal and nuclear. Is that okay? Right? It's not directly the heat, but it's the heat converted into pressure, and then that pressure forcing the turbine to rotate, and which is what is producing electricity, right? And therefore, once you rotate it, then you know there is still this same water you want to recirculate. So there are these chiller towers and so on, which you would have seen in typical power plant, right? and then the same water again comes in here, again gets heated up, again converts to high pressure steam, and then this keeps on happening. Because you don't want to use fresh water or you don't want to waste water and keep doing it, right? So you can recirculate the water. Any doubt in this one? Yeah, of course there are lot of mathematics there related to how much should be the pressure, if this is the pressure, what will be the force and whatnot, but I think that goes more towards the steam cycle and so on, which we will not cover as a part of this course, right? We will focus more on converting this mechanical energy into electrical energy and then how it goes into the power system, but this is the basic thing. This is for coal and nuclear. Here you use synchronous generator. What is the other source? What was the other predominant source in the list we saw? Yes, last lecture we saw a list, right? What are the other sources other than, there was gas. We don't use much gas, we don't probably have much gas, I am not sure which way, but we don't use much gas, right? But some of the other countries use quite a bit of gas. In gas, of course, you could have done the same thing, right? You could have done the same thing. You could have used the gas to boil water, convert it into steam and then use it. Or you can, just directly burn the gas and because it can burn with a sort of a pressure, that burning itself you can use to propel, right? Think of it as, or imagine a jet engine, right? So what is happening in jet engine? You're burning something and that is making sure the engine rotates, right? So something similar. So you can directly burn it and you can rotate something because of the pressure of that burning. So there is usually gas can do just directly by burning, right? It's, let's say, imagine it as a sort of a pressured burning, have a turbine which will start moving because of that pressured burning, right? Something similar to what happens in an aircraft, right? In a jet engine of an aircraft. Is that okay? And then again, once something moves, you connect the same guy. You connect this guy here also, right? Once something moves, you just connect a generator and it will produce electricity. Coal, nuclear, gas. What else? Diesel. Okay, diesel is also used. What did you say? Hydro will come to, okay, but let's first see diesel. Yeah, there may be small diesel generators, or if you have heard of DG sets, right? What do they do, or how does they produce electricity? Again, you burn this fuel, right? Again, you could have done this way, but it's much easier. You have an internal combustion engine, you have an IC engine, so you burn it in an IC engine, convert the linear motion into rotatory motion, correct, again the same guy, right? We will get the electricity. Next was hydro. Right, you have water there at a high level, at a high height, right, and you let water come down from there through some channel and then it will gain kinetic energy, and now you use some sort of a turbine, this water will hit the turbine will move, you have a rotary motion and then you use a synchronous generator to convert that rotary motion into electricity, right. What else? What else? What are the other sources? Solar, okay. So solar, when it started, there were like two technologies which people were sort of thinking of, right? If you see 20 years back, there is of course solar photovoltaics, right? You can just call it solar PV, and then there was solar thermal. So what are these two? These were the two, sort of competing technologies for solar when it started. I forgot to put my phone on silent. So if you see solar thermal, the idea was simple, that sun has heat, right, but of course this heat is not too much. If you just leave a glass of water, it would not boil and produce a steam or something like that, right. But if you can concentrate this heat using some sort of reflectors, then maybe at that point you will have substantial amount of heat you can let the water flow through that concentrated point, it may convert into steam, create pressure, you can use that pressure to run a turbine which will produce electricity, right. So this idea was actually quite popular at one time, and you can imagine why, right, because every time, the way, if you logically think, right, then how would you think, okay, look, we have 80% of the parts, right, we have this guy here, we have this guy here, we have the synchronous generator, we have 80% of the parts. The only thing we have to do is just get the solar rays to concentrate at one point so that there is sufficient heat there. So you just have to build some sort of reflectors or concentrators or something like that, right. So you only need to do 20% and you will have a system up and running which will produce electricity using chlorothermal, right. When we say we have 80% of that, doesn't mean that we have them, but we know the technology, so to speak, right. So if you imagine 20, 30, 40 years back, you know the technology of rest of the things, right. You only have to sort of build a technology for concentrating the solar rays and that would work, right. But in reality, this particular technology did not become as good as the other one, right. And now if you see globally, this is the dominating one. This is of course a completely different technology. So what happens in solar photovoltaics? Solar photovoltaics, you have a solar cell where there is light which starts. It's not the heat which is there in the sunlight, but it is the energy particles, right, which excites electrons and holes and creates electron hole pair in this silicon cell, and which leads to electricity, right. So there is no moving part. We are not using the heat, you are still using the energy, of course you have to use the energy, but you are not using the heat which is available. In fact heat is a byproduct of this, and you don't require a synchronous generator, you don't require a turbine, you don't require water, you don't require a big concentrator, right. So all of this is gone away. So you see, this is the one which is completely different from the rest of the technologies, right. This is the one which is completely different from rest of the technologies. Again, this course we don't go into too much of details of how this conversion gets done, but if you are interested, you can watch something on YouTube, you can take some lectures, some elective courses later on to learn more about photovoltaics and how they operate and what are the challenges and so on. But this is, so when yesterday we saw the solar, right, how much was that value? I think 100 gigawatt or something, if I remember correctly. So we saw it, right, maybe 100 or 60 gigawatt, something like that we saw. But that is all predominantly solar photovoltaic, right? People don't use this. Any reason why people won't use this? I think this we have probably discussed also, right? You can imagine this has to be a very big and bulky system, requires a lot of maintenance, lot of operations. You need to hire 20 people, be there on the ground, always making sure there is no leaks, there is no, operation is proper, boiler is proper and so on. But if you talk about photovoltaic, you just buy one panel and you connect it to the grid and starts working, doesn't require anything, no maintenance, no moving parts, right. So it works really well. Okay, any other technology for power generation? Wind, yeah, wind is another one of these guys. Yeah, you have wind, you take wind turbines which will rotate if the wind flows, and you rotate a generator, right. So again, wind does connect to the synchronous generator. Now two things to observe here. First is that although all of these guys are using synchronous generator, right, including solar thermal, but then all of these technologies would not rotate the synchronous generator at the same speed. For example, if you have steam based generation, right, then usually steam would be at a very high pressure and the shaft would rotate at a very high speed. But if you are talking about hydro, for example, right, the speeds would be relatively low. Wind, if you see, you can visibly see this guy like slowly rotating, right. It has huge amount of torque, but the speed is very slow, right. So there are some technologies which would require a higher speed synchronous generator. There are some technologies which require a low speed synchronous generator, right. So this one you can make it to be high speed or low speed. I'll come to more differences about this later. And essentially what is the meaning of speed? You remember this formula, Ns is equals to 120 F by P, right? You remember this formula? What was this formula about? This was what? This was the formula for synchronous speed, right? In synchronous generator, as the name suggests, is always operates at synchronous speed, right? Induction motor would always operate at non-synchronous speed. At synchronous speed, actually the induced voltage is 0 and therefore no torque, right? Good, you remember, some of you. But the synchronous generator part always operate at synchronous speed. So therefore, if this is the rotor speed, right, you would always want to have frequency of 50 hertz, right? If you are living in India and if you are living in US, let's say you always want it to be 60 hertz. Some small variation is okay, but you don't want it to change predominantly, significantly, and therefore, for high speed ones where n is large, you have to keep p small to get f of 50 hertz. When your speed is low, you would have large number of poles, right? So therefore, this low speed would require large number of poles. 1 second. And high speed would require less number of poles. So the technology is same, but the motor category is the same, but it's not like, you cannot use the same exact same motor there versus here. It would depend on the speed and then the frequency that you want, right? And accordingly you will decide the number of poles. Good. Okay, so what I'll do is, maybe today today I'll probably talk about the basic construction of a 2-pole machine of a synchronous generator, right? But there is one online video on YouTube recorded by my colleague. So I will share that on our Moodle. So maybe you just tell Nikhil to post it. There's a YouTube video made by, I think, Professor Kulkarni, Anil Kulkarni. We can post it. So that one is a 4-pole machine, right? So at least that will tell you the difference. Or if possible, next time I can play it here, then all of us can see. But anyways, come back, that's a topic to be discussed a bit later. For now, yeah, so different technologies would use different types of synchronous generator, right? And as you understand, if something is rotating at high speed, right, you would have to maybe change the geometry slightly because there's a wind drag, right? If you have something like a rod rotating at high speed, it will have a lot of drag, but if you have a cylinder rotating at high speed, it will not have a drag, right? So all those minor details come into picture between these two speeds. So that is one point. The second point to observe on this board is that which of these you can start instantaneously. You remember, right, this was a topic which we were discussing in the beginning, because loads keeps on changing. So and always in conventional grid, at least there was no storage, so always the generation has to match the load, right? So if suddenly loads go down, the generation has to go down, suddenly load comes up, generation has to come up, right? How we conventionally took care of that is we kept some systems running all the time, even if they were not producing any power. So those were called as spinning reserves, right? Those were called as the name suggests, they are spinning and they are reserved, right? It could be a dedicated generator completely on as a reserve, or it could be one generator which is whose 80% or 70% of the capacity is being used, but remaining 30% we could have drawn it, but we are not drawing it and we are keeping it as a spinning reserve just in case some load comes up suddenly, right? That said, you cannot schedule it for the whole day, for example, right? In the whole day your loads will change drastically. If you want to keep the spinning reserve, that's like unnecessarily you are wasting your fuel. So yes, you want to have some reserve because you don't know what will happen in the next 5 minutes, but you don't want to have a reserve for the whole day, for example, right? So what you do is you do some form of balancing between the spinning reserve and little bit of scheduling, right? So you know that, okay, this is how your load profile would be. You would have more load coming in the evening, and therefore in the evening you would like to turn on some of the generators. Maybe in the afternoon time you don't want some generators, you can shut them down, right? So spinning reserve plus some amount of scheduling can give you more optimal, sort of cost saving or fuel saving. So, which of these technologies you think can be turned on and off really fast? We have all the technologies on this board, predominantly what is being used today. So, which of these is really fast? Sorry? Yeah, photovoltaics you can just turn on anytime, you can turn off anytime. The only problem is that you don't have a control over how much power it will produce, right? You can turn it on at night, no problem, but it will not produce anything, right? But you can shut them down really fast, right, during the daytime. So yes, this is like very fast, but you cannot get the desired power as you would want, right? But this is certainly very fast because there is no moving part, it's all just a semiconductor, power electronics. So, things can happen really fast. Things are actually switching at megahertz, kilohertz frequencies. You can do things very fast here. Okay, what are the other ones relatively faster now? Diesel, yeah, press the button and then engine starts, right? You can start diesel very fast, but the only problem with diesel is that diesel is not predominantly used for bulk of power generation, right? So, hardly any diesel would be synchronized to the grid. Diesel would mostly be used for remote areas where there is no grid. So, you transport diesel, you run a DG set and get a power, right? So, these guys are not usually connected to the bigger grid. So, but they are nevertheless, they are relatively, I would say, let us say not very fast, but then they are not connected in the grid, so usually not grid connected. Okay, now coming a step ahead, which one? Yeah, hydro you can do fast, absolutely, you can just open the tap and water will come and then it will start producing. What else? Gas again, yeah, it's like you are burning something and rotating. All of you sit in, if you have been in aircraft, you see it starts, right? It like hardly few seconds or something. So it's also fast. Okay. Wind again, wind you can make it fast. It's same as solar photovoltaic. You can make it fast. But you will not probably have a control. If you want more power, it's not that it can give you more power at your demand, right? It will give you the power what it can. It cannot obey your command or reference. These two guys are really slow, right? The coal and the nuclear, because of the process you can understand, right? There is a heat to steam conversion which will take time. Once the steam builds up, then it will start rotating turbine. So these are like very slow processes. So you don't usually in a day, you would not turn on and turn off these plants, right? They would just keep running. And therefore, sometimes you also call them that they take the base load. Base load means they are the one heavy lifters, right? They are the one who are actually supporting. Then these guys will keep running throughout the day. You don't want to shut them down. You don't want to, power them up within a day. But then, for example, hydro, you can easily do it, right? Evening time, you can you can, remove the valves and it can produce power much faster. And so for gas also relatively, you can still turn on and turn off in a reasonable time. Yes and no. You would, you would directly burn gas and use it to run a turbine. Once the turbine is rotating, whatever comes out of the turbine is still relatively very hot. That you can use as a secondary cycle to build steam and then run a secondary turbine. You can do that, right? So you can have a direct burning plus a steam sort of a cycle there for gas. It has a specific name, some combined something which I'm not able to recollect, but you can search it. But yeah, so you do that with gas to improve the efficiency, right? Because the gas coming out is still hot, you can still use it and produce steam. So you can use it in sort of improve the efficiency. Correct. Any other question here? Okay. So you have spinning reserves plus you can do scheduling. But now the problem is there is earlier, most of the loads were relatively predictable. Now you have loads which are highly unpredictable. Over the top of that, now you have generation, which is really unpredictable, right? Solar, suddenly a cloud cover comes in and then power just goes down, right? Wind, if wind is flowing, wind is not flowing, suddenly power goes down. If you have one small wind in the whole India, doesn't matter, right? Because everything is connected, 1 kilowatt, 10 kilowatt, 50 kilowatt here and there would not matter. There are these huge hundreds of megawatt of generators running, they won't even mind, supplying that small variation. But then now as we keep on increasing the solar and the wind in the system, right, that unpredictably related to the solar and the wind, in a way again requires you to either have spinning reserve, right. You can do scheduling as much as possible. For solar, a little bit of scheduling you can do. During the day you will have sun, night you won't have it. But in day also there could be cloud cover, there could be rainy season, suddenly storm coming in and then power going down, right. So you can do scheduling or you would require a spinning reserve, right. Now spinning reserve, as we understand, it's expensive, right. You are unnecessarily burning the fuel even if you are not drawing any power. So the substitute to this is storage. Substitute to this is storage. You can keep running some generator plus have solar photovoltaic, right. Let's take an example. Let's say this is 50 gigawatt, right. Of course, 50 gigawatt would be or 60 gigawatt would be distributed in the country. So it's not that suddenly 60 gigawatt can be sort of go down. But then it is possible that predominantly it certainly lies in Gujarat, Rajasthan, Maharashtra probably. And then there could be a storm, let's say, coming from this side, and then these three sort of goes down, right. You can still do scheduling, you can still do prediction, you can turn on some of these guys a day or two before you think this will happen. But if something happens suddenly, then the only way to take care is have a spinning reserve. That means have a coal plant running, multiple coal plants running without even producing power. So they are still polluting, doesn't really add up, right. So people are talking about now using storage, which would substitute for, which is like a substitute for spinning reserve to some extent, right. Storage could be batteries, storage could be hydro, right. These are, there is compressed gas storage as well. So these are different types of storage technologies people are talking about, which also is slowly getting integrated into the grid. As of now, we don't have much storage in the grid, but as we move forward, of course, we expect lot and lot more storage to be integrated. You can imagine in future, if you want to completely get rid of thermal power generation, especially let's say coal, maybe to some extent nuclear also, gas also, then you have these guys, right? You have these guys, you have wind, hydro and solar, right? Except hydro, these two things are highly unpredictable. So you have to have significant amount of storage built into the grid if you really want to, sort of achieve that vision. And thanks to improving battery technologies, right, the prices are going down. It's becoming more economical to have it. Still, it's being done at a pilot level. So if you go back and Google, you would realize that most of the countries globally have tried some sort of a pilot, means a small steady project of integrating storage with their grid. It's still not widely used, but as the prices are further coming down and these technologies are getting more and more integrated into the grid, you would see that storages would also come up. Okay, now go ahead. What are the questions? Yes, so that is called as hydro pumped storage. That's called as pumped storage. So you have 2 containers of water. You when you have excess power, you pull the water up to a vertical height, and then if you don't have it, you further let the water come down and use that as electricity generation. What according to me is the which source of energy? Sorry, what did he say? Cleanest source of energy. Yeah, it's a difficult question, huh? It's a difficult question which I don't think I can answer, which is the cleanest source of energy, right? It's a very, very difficult question. I'll answer it a little bit later because it's a difficult question. But your question? Go ahead. So go to the second one. Yeah.
running and you decouple it, it's not providing energy, it is producing electricity. Where is that going?
Yeah, it's not. So we will see by end of maybe not today, but by end of next class, you would understand that a synchronous generator can run and does not produce any power. It can be producing maybe reactive power or maybe no active, no reactive power also, right? It can do it. So, but we'll see it in the next class, you would know.
Providing energy to what's the problem with the decentralized system? I don't think I've said.
So we have a lot of them. So if you see how many, I don't have the number, but you guys, maybe one of you can Google it right away, right? How many thermal power plants we have in country? There will be a huge number. It's not only few, it's huge number. Can somebody Google it now? How many thermal plants we have? Yeah, you are using phone, go ahead. How many power plants we have in India? How many thermal power plants we have in India? How much? Some 300 or something. A large number.
The reason we talk about photovoltaics and all that they're getting starting about, but it's the reason because the reason that they're better than this, or it's because the government is doing.
Okay.
How good are they compared to solar?
Which one?
Cost per
Which one? Solar.
photovoltaic.
Photovoltaics, yeah. So now her question is that, you know, why are we using solar photovoltaic, right? There is a term called grid parity. There is a term called grid parity. What it means is, if you are getting 1 unit of electricity from solar, what is the cost of it versus what is the average cost of getting 1 unit of electricity from the existing grid. And if the solar per unit cost is lower than grid per unit cost, that means you have achieved grid parity for solar, which globally has been achieved much before. So already electricity from solar is cheaper than what you draw from grid, and that is the reason almost all governments across the globe, right, they would want people to put more and more solar, because that would reduce centralized burden on building these huge power plants. So save in terms of a centralized focused capital investment, right? These are like very expensive, right? So everybody, you know, therefore wants to promote it, in addition to the environmental, you know, benefits what it carries, right? That's, yeah, so that's a secondary thing. But if you see purely based on economics also, right, it makes a lot of sense. There's a little bit of catch. The catch is these guys are not controllable. So in the beginning, you know, all these power system operators were quite a bit worried. They thought, यार तुम ऐसा nuisance सा कुछ source लगा दोगे system में, तो कभी power देगा, कभी नहीं देगा, उसकी मन आएगा नहीं देगा. Then the problem is, how will I control the system? And if the whole grid goes down because of that, it's like you guys will shout on me, right, as a system operator, क्या किया तुमने? So therefore, initially there were people had big concerns about integrating these variable generation into the grid. Right? But over a period of time, people realized that they can be managed, they can be controlled up to a certain penetration level. If the penetration of these sources becomes even larger, you can go to some sorts of storage technology. So people are, as we are sort of moving towards more and more renewable integration, and there is like things evolving. There's another good example, if you are, since you are talking about this variable thing, right? So Denmark has a lot of wind. It's very windy. If you go there, actually it's literally very windy, but it has a lot of wind generation, and Denmark doesn't consume so much of electricity, right? So therefore it exports to the rest of the Europe. So you can always, so, you know, having a bigger grid helps in taking care of these unpredictable sort of, you know, sources or loads. But in addition, you can go for spinning reserves, you can go for storages and so on. So spinning reserve means you have a generator which is spinning. So you have this steam built in, you have this water boiling, you have all the systems set in, you know, it's running. It's not producing any power. It can produce power really fast, because already steam is there, already rotor is rotating, already everything is set up, right? It's spinning, but it's reserve, it's not producing power. That's what we call it, spinning reserve. Any more questions? I think so. Maybe people would have tried. Yeah, I think there is something. Tesla कुछ था क्या? Kite उड़ा के किसी का तो था ना? Benjamin Franklin का था. But yeah, I think people have tried. But look, for these technologies, the idea is that it has to be. It is possible. Maybe we don't know that. It's possible. But you want a large source of energy, right? That is the predominant need in all of them. Maybe it's possible. As of now, there's not much, but there's nothing like that I know of at commercial scale. But maybe it's possible. You can look at it. Okay, any more questions? Okay, if no more question, let's answer the difficult question. So, what was your question? Difficult one? Is it really clean? Yeah, which is the cleanest source of energy? Anyone, which is the cleanest source of energy? Which is the cleanest source of energy? Go ahead. Who says? Somebody said nuclear. Who said nuclear? Okay. Any other one? Anyone else? What is the cleanest source of energy? Okay. So, if you see in absolute sense, right, whatever you do, there is a reaction to it. There is whatever positive you do, there is something negative happening because of that, right? You imagine, this industrialization happening, and people thought that what a great idea, you can, why are you using wood? You can use this iron and make much stronger weapons, and you can make much stronger structures and much rigid structures. But then, do you have iron? Yes, we have a lot of iron. खोदो, खोदना चालू किया. Now, खोदने के बाद you found few things, but that you cannot directly use. So you have to now purify it, right? खोदने में you need energy. Purification requires energy. In the process of purification, you would end up emitting a lot of pollution. For example, if a purification process requires heating, right? Let's say you want to melt something. You guys have learned it, na? Somewhere I think you would have studied, maybe in 11th, 12th, how do you make, you heat the thing, the whole rock, and then it gets decomposed, then you somehow try to collect the useful metal. What is it called? Some metallurgical things, right? So you require a lot of heat. Again, you would maybe burn coal, maybe not burn coal, maybe use electricity. Then, once you do the metallurgical process, then there may be a slurry of water and other elements which you don't want. And now this guy is there, you have to do something, you have to dump it somewhere. So you see, even, using iron for that matter was not so called clean. The environment was much cleaner before we started using iron, isn't it? So with every technology this happens. The same thing happens with solar photovoltaic, because you need materials, you have to process it. The processing would require itself some energy to build those panels. So there's always a catch. But that said, it's not that, you should not do anything at all. You still have to evolve, you still have to continue exploring cleaner ways of doing it. There are, if you want to read more about it, there are a lot of books, there are a lot of non-technical books where you can read more about these topics, right? Yeah, but let's not discuss beyond this point here. Yeah. No, that is not the case. That is not the case. It is not using the same energy which has gone into making it. It is using the energy which is coming from the sun. Yeah, so you can, so yeah, so you have to do the math basically, that how much of energy you used to make it, then how much of energy how much of pollution you incurred in making it, and how much pollution you are saving when you are using it, and then that has to be come out to be better, right? Okay, I think enough of a board with no equations. We'll learn it in the subsequent course. In the subsequent lectures, we'll learn about it, right? Okay, I think let's move on and let's learn a little bit more about synchronous generator now. Okay, how many of you are coming today evening for the lab visit? Okay, so you guys have seen your group. The other group has also gone to a substation, other batch. Do you guys know about it? Huh? Do you also want to go there? Maybe you do today's visit in the labs, then we can discuss. If you also want to go there, then we'll also schedule similar things for going there also in one of the, 1 hour, 2 hour, not more than that, not take too much of time. Okay. So you have a stator, you have a rotor, right? Any rotating machine would have a stator, would have a rotor. In synchronous generator, the stator, which is the outside part, is the same stator which we used in induction motor, right? It's exactly the same stator. You remember induction motor, we had one A phase winding, B phase winding 120-degree phase shifted, and C phase winding 120-degree phase shifted, right? So it has exactly the same stator. Stator is same as of an induction motor. In induction motor, the rotor was made up of, what was rotor made up of? What was rotor? It was squirrel cage, right, or wound rotor. Essentially the rotor had its winding, and because of the stator field, there is a voltage induced in the rotor which leads to the current that produces the field again, and the two fields interact and produces torque, right. That was the basic principle of an induction motor. All of you remember this? Okay, so therefore induction motor could never operate at synchronous speed, because if this guy started rotating at synchronous speed, right, then field is rotating at synchronous speed. What is synchronous speed? 120 F by P. If field is rotating at synchronous speed, rotor is also rotating at synchronous speed, then if you are sitting on rotor, you would see that the field is not changing. So no voltage is getting induced in the rotor, no current, no torque. And therefore induction machines never operate at synchronous speeds. Now you come to synchronous generator. In synchronous generator, rotor is the same. In stator, either you can have a permanent magnet based stator, or you can have a winding coil and excited with a DC current, so that it behaves as a north pole and a south pole. Is that okay? So in synchronous generator, the rotor is excited using a DC current or a DC voltage, right? If it's a wound rotor, if it's just a permanent magnet, there will be north and south. Now in which case we use permanent magnet, which case we use electromagnet? If you talk about, let's say, electric vehicles, right? Which type of motors does electric vehicle predominantly use? You may have heard across this term called PMSM, right? What does it stand for? Permanent magnet synchronous machine, which is the same with permanent magnet, right? This permanent magnet synchronous machine, permanent magnet synchronous machine. So in EVs, what you see is permanent magnet synchronous machine. Same machine when you are using as generator in big power plants, which are of the rating of megawatts, right? It's difficult to mount those huge powerful magnets. Expensive to buy, of course, difficult to mount them, right? Because there will be huge force. They may come out, they may get stuck in some other metal. Moreover, you do want to have some control over the magnetic field, which with permanent magnets you cannot do, right? But if you have a wound rotor means rotor with a winding, wound rotor, right? If you have a wound rotor, then you can control this current and you can change the field, which you could not have done in a permanent magnet, right? So permanent magnets rotor is used usually for low power applications, mostly for motoring mode. For generation, especially for high power, you use wound rotor. Wound rotor means you are winding. Is that okay? So wound rotor versus permanent magnet. Wound means there is a winding, maybe a DC, maybe a AC. In this case, we give DC, of course. Induction motor, we had a wound rotor where we were giving AC through slip rings. So wound means it's wound, that's it. Okay. Now what it does is, let's say if this is the geometry, right? This is the geometry, and I am giving it, there is nothing, I am not giving any current to the stator winding, I am giving a current to the rotor north and south, right? How will be the flux in the air gap because of this? How will be the flux in the air gap because of this? How will be the flux in the air gap because of this? The flux will be, is an electromagnet, flux in this direction, so flux is that okay? That's how the flux will be, right? There is no current here, only in the rotor I am giving a DC current, so it is producing flux and it is going like this and then through the yoke, through the remaining stator it is coming back and then again going back from here, right? You remember the geometry? So the flux is crossing air gap from rotor to stator, stator it will go back from the yoke and then come back and enter from the south pole, right? Any questions so far? Okay. Then now imagine I connect this to a shaft and I put a turbine there and the turbine is rotating, this shaft is rotating, right? And now if this shaft is rotating, this whole flux pattern is rotating, right? And I have a coil here which I have kept it open loop, but there are N turns. So this N turn would have a voltage induced in it, right? This stator coil AA prime will have a voltage induced into it. For now you just imagine there's just one coil here. Let's assume one turn just to make it simple. There is one wire and that's it, right? So this one turn here which is going in from here, let's say coming out from here, will have the flux linking this turn is changing. Is that part okay? How can you see this? The flux linking this is the flux crossing this direction. If the rotor is in this position, the net flux crossing this is 0. But if the rotor is 90 degree, the net flux crossing is quite a bit. So therefore, as the rotor rotates from this position to 90 degree position to 180 degree position, your flux linking the coil is changing. And if you do Faraday's law, if you apply Faraday's law, E equals to N d phi by dt, you will get the voltage induced. Is that okay? If you apply Faraday's law, you will get the induced voltage. So that is the basic principle. Once you have the voltage induced in this A winding, right, you can bring it out, you can connect to the load and this acts as a generator. Okay, any question, any doubt so far? Oh, using the turbine and any of those guys which we have listed on the left side? No, go ahead. Maybe your question is correct. Go ahead. Yeah, you leave that shaft part, you put the wires. Anyone else feels? So she's thinking that, you know, how will you rotate it? Would it somehow crisscross the wires, break the wires? What do you think? If you rotate it, right? If it's a permanent magnet, you are just rotating it, all of us can easily imagine, right? There's a permanent magnet needle or something, you are rotating it, no problem. Here there are wires. Now this wire is connected to this source. Let's say this is battery. So now if you put this battery onto the rotor, you can rotate everything. But if this battery is not on the rotor, it's stationary and this guy is rotating, then of course if you twist, then the wires will get messed up and they will eventually break because of the stress, right? Is that okay? Not okay? Not okay. This is stationary, this is moving, right? If this guy is rotating, this guy will try to pull this wire, it will break, right? So either you can have both the battery and the rotor both sitting on the rotor and then everything is rotating, no problem. But you cannot have one guy rotating, the other guy is stationary. So what do? Slip rings, right? You use slip rings. You remember slip rings from DC machines, slip rings from wound induction rotor, right? The wound induction rotor also had slip rings. So you use slip rings. Slip rings is basically a mechanism where you have something rotating and a stationary part which is connecting to that rotating part. right, using a certain force, and that's how the current is getting transferred. So even if this part is rotating, the stationary part is stationary, right. So you can have now two slip rings, one for the positive terminal, one for the negative terminal, and you can connect it to the battery. So you would, for this connection to happen, you would require slip rings. Slip rings were used in DC motors, slip rings were used in, no, slip rings were not used in DC motor, so to say, they were used in induction motor, wound rotor, right. Did you see slip ring in the, in the lab somewhere? You must have seen. Okay, but maybe I think I showed you some pictures in the last course. You can Google it and see the image of a slip ring, and that should tell you a little bit more about that. Yeah, correct. So there you would have seen it. Yes, so that open motor cut set motor sort of experiment, right? You would have seen the slip rings.
The field will never complete the circle. As soon as you not complete, we go up again. Never complete the circle.
You can. That's why we are putting slip rings.
So they're connected before, right? And then you move this and then you connect again there. So then you're not moved here and then you put it.
You take the wire from inside the rotor and connect. Don't take it from outside the rotor. Rotor hollow, take it from inside and connect to the slip ring. You can do it. Your wires will not cross. You can do it. Why? A slip ring. It's not brushes and commutator. Brushes and commutator had two different electrical sections, right? Sometimes the brush was connecting this part, sometimes the brush was connecting this part. This is a slip ring. The whole ring is a single section and the brush always touches the whole of the ring, right? So it's a slip ring. It's not a brush and commutator assembly, right? Okay. Let's take a step ahead, and now a question which I last start asking from there. So the question is, what will be the nature of the voltage induced in the stator? What will be the nature of the voltage induced in the stator? Is that okay? What will be the nature, or what will be the waveform, or what will be the shape of the voltage induced in the stator in this case? As I am rotating the rotor in any direction, clockwise, anti-clockwise, with a constant speed I am rotating, what will be the voltage induced in the one turn of the stator? Single turn. Sinusoid? Okay, why do you think sinusoid? Yeah, but anything can be changing. It's not only sinusoid which changes, right? You can have a triangle wave, you can have a square wave, you can have n number of shapes which can be produced because of the changing field, right? Want to try? Sinusoid? 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 No answer. Sinusoid? Sinusoid? No answer. No answer or sinusoid? Sinusoid. Anyone who thinks this is not sinusoid, raise your hand. 1, 2, 3, 4, 5, 6, 7, 8. Okay, go ahead at the end. Why do you think this is not sinusoid? It will be periodic but not a perfect sine. Okay, then next person. What can it be if not sinusoid? It can be trapezoidal. Yeah. Why do you think it's trapezoidal? It could be trapezoidal. Okay. One bola. It will be trapezoidal. Okay. And the rest of you guys? Quasi square wave. Trapezoidal. Okay. Quasi square wave. What about others? Okay. So if I plot the flux linking the turn in this case, right? And if I assume this is theta equal to 0 position, the flux linking is 0. As the rotor rotates in this direction, the flux linking the turn will increase. Now if you see the way I have drawn it, this one, right, you remember when we were learning DC machine, it had lot of relevance of how is this shape. Why? Because the way I have drawn it, the shape as it is, if you see, it appears this is uniformly width, right. If it is uniformly width, that means the reluctance at each point is the same. That means if this is producing some total flux, that flux will equally divide between this complete region, whatever, let us say this is some angle, right, it will completely divide in this angle. That means now if I am rotating, the increase in the flux is linearly related to the rotation. Is that okay? So if as of now it's 0, if I rotate it by 1 degrees, you will have some one line and one line coming cutting and then one line of flux flowing in the linking the flux. If you rotate it 2 times, two lines cutting from both sides. If you rotate it 3 degrees, 3 lines and so on. So the relationship between the linking flux linking and the theta is linear because this is uniform. Because this is uniform flux. Is that part okay? Not okay? Should I repeat? Right? These are, let us say each, this is same flux, the flux throughout this point is same, right. So if I define this as theta equals to 0, right, you can see that from minus whatever delta to plus delta, the air gap flux is same, and therefore if I now rotate it, whatever you know, if I rotate it by angle 1 degree, you will have certain flux linking this crossing this turn. If you rotate it 2 degrees, you will have double the flux. If you rotate it 3 degrees, you will have 3 times the flux, because more and more lines will start coming here, and they are of each line represents each equal flux, right. And therefore as you are rotating it, your flux is increasing linearly, right, till this point comes and touches here. After this point, this is blank. So therefore, even if you are rotating, the flux is not changing for some duration, and then again it will start reducing and reducing, and then again it will be blank, and then again it will start increasing. This is how the flux would look like if I assume what I would term it as a uniform air gap flux density. Uniform air gap flux density. FO if I have a uniform air gap flux density, that means the flux density here, the flux density here, the flux density here, everything is same, and that will happen if I have a uniform air gap, because all the reluctances of all the paths are same. So flux will equally divide. So I'll have a uniform flux density. If you have a uniform flux density, this is how the flux would look like. Of course, if this is the flux, then now you can plot E. How would E look like? E is N d phi by dt. So if this is like this, so E will be positive, 0. Yeah, this is the voltage induced. Is that okay? So for every theta rotation, you have n number of lines coming in from right to left. So your flux is increasing by n. So if you do 2 theta rotation, you have 2n lines coming here of equal strength. So your flux increases proportional to 2n, which is proportional to theta. What is it called? Square wave, quasi square wave, trapezoidal, which is is quasi square. Good. Is that okay? It's not sinusoidal. Are you all fine with that? Yeah, but for now we are getting square wave. We'll come to that, we'll come to that, wait, we'll come to that. So far is it okay? No, this is not based on any previous understanding, they are just seeing, if it rotates. Because flux density is uniform. So these lines are placed at equal spacing in a way. So if you are rotating by theta degrees, if n line comes in, if you rotate 2 theta, 2n line will come in. Each line corresponds to same value of flux density, right? Because the flux density is uniform, uniform air gap flux density, right? That is the main part. Okay, now what? Just try to redraw. Yeah, it looks like an egg, it's not an egg. Huh? This is supposed to be a circle, the outer one, so let's just focus on, this part. So this is rotor, this is stator. Okay, I am just focusing on the top part from that figure, right? This is rotor, this is stator. And now if you see, I have tried to draw a different shape of stator. Rotor is still circular, right? Sorry, the stator is still. Lot of confusion. Ruk ja bhai. Just wait for some time and come back to it. Huh? So this is rotor, outer is stator. Stator is still circular, right? The rotor now I have tried to change the shape so that the air gap is no longer uniform, right? Air gap is no longer uniform. There is small air gap here, and as I come to the remaining part, the air gap increases, right? So I have shaped the rotor such that there is small air gap here, and as I come on the side, the air gap increases. Is that okay? Now, if you have winding here and if you have some net flux which is flowing here, how will it cross the air gap? Will it be uniform? Will it be uniform? Will the flux crossing the air gap, will it be uniform? Will the same flux density exist here? Of course, the flux will cross in this way, right? There is no question about that. But the question is that will the flux density across this part, will it be uniform or no? No, right? Because here reluctance is what? Small, less, because lesser length of air gap. Here larger length of air gap, so reluctance is more. Smaller length of air gap means more flux will flow through this. Larger gap means lesser flux will flow through this. Is that okay? So larger air gap means lesser flux will flow through here, more flux will flow through here. Now, if I somehow, decide the shape of this guy, I can get a flux in the air gap which is sinusoidal. Earlier my flux density was uniform, now I can have a flux density which is sinusoidally distributed in the space. Is that fine? And now if I am rotating this, you are doing integration or you are doing derivative of this flux in one way or the other, and therefore the induced voltage also becomes sinusoid. Is that okay? Earlier you had a constant flux density, so if you rotate it, you get that kind of wave shape. Now you have sinusoidal flux density. So if you rotate it, right, you do E equals to n d phi by dt, derivative of that sinusoidal or that cosine would eventually lead you to a sine or a cosine, right. So the shape of the voltage induced is now going to be sinusoidal. We will try to write the expressions, we will try to derive it also, but Do you get the sense? You get the sense of what we are talking about here?
Even with a uniform distribution, you still get a sinusoidal.
Yeah, that we'll anyways do, but we'll come to that. Why are we doing all this? Okay, I'll try to answer it. Wait, I'll try to answer. But for now, is this okay? Does it solve the problem? Does it lead to sinusoidal flux distribution, which leads to a sinusoidal voltage injection, right? So here you get sine flux distribution in air gap leading to sine right. We will do the derivation in the next class hopefully, but is this part clear? By shaping this rotor, you can have a variable air gap and you can create a sinusoidal flux distribution, right. And now if this rotor rotates, right, it is non-uniform. Here if it rotates, you will have lot of flux lines coming from right to left in a theta degree rotation. But if this point comes vertical and now you are rotating same theta, only small amount of flux will change, right. So therefore you can get the sinusoidal induced voltage instead of a square wave one which we got earlier. Is that okay?
If I have 4 lines, let's assume that the 2 lines are replaced for lines. How to utilize lines are taught. If I take a component of that along this line, the component of the new 2 lines is not remain the same as the component of the
remain the same because all those 2 lines are flowing through this. So when you see what are the flux crossing from right to left or left to right, it's not the direction of this air gap flux which matters much. It's that how much of net flux is crossing this line. This is the coil. So how much of net flux is crossing this depends. So which is what flows through this part, right? So if you take these 2 points, it's the flux crossing this which matters. It doesn't matter. Lines would most likely be normal because that's a minimum reluctance path. Na? Lines would most likely try to take the shortest path. You don't have to take the cost component. Okay, you go back and do one thing before the next class. Lecture doesn't end, I continue, but I'm saying before the next class you do one thing. You have a look at the DC motor initial lectures of our previous course. And you would see that we did consider two types of magnet shapes there, right. In one case, you would get a rectified sine wave kind of thing. In other case, you get a square wave. It's exactly the same thing. They're just revising the same thing. Of course, we didn't record those lectures, but it is exactly the same as what we discussed in the beginning of course 114, right, when we were talking about DC motor, the first few lectures of DC motor. You can go back and have a look at it, then we can discuss it again if required. But if you have a sinusoidal flux distribution and if you now rotate it, you induce a sinusoidal voltage. You can have 2 ways of doing sinusoidal flux distribution. One is this way, you can have a rotor of this shape. This is of course a 2-pole rotor, you can have multiple poles also. The other way is you can have a rotor which is still circular, right, but the winding you would do is you do winding in this side, then you do winding here, then you do winding here, then you do winding here, and so on, right. So winding is like this one, this one, this one, this one, this one, and this one, right. If you see, this also induces the flux in this air gap to be sinusoidal in nature, right. So you can either do it by using a cylindrical rotor with a wiring arrangement, or you can do it with a what is this? This is called as salient rotor. This is called as a salient rotor. You have to remember some names. This is called as cylindrical rotor. So you can use either a cylindrical rotor or a salient rotor. The bottom line is you want to create a sinusoidal flux distribution in the air gap. Once you have sinusoidal flux, you have a sinusoidal voltage, and that's what we want, right? We want the output to be sinusoidal, not square wave. So next time what we'll do is we'll start from assuming there is a sinusoidal flux distribution, and from there we'll try to derive the induced voltages. Is that okay? Okay, let's stop then.